Homework? Yes? I am going to collect that at the beginning here, but I'll talk about at least one of them. Let's just be clear on what we're doing today. You're going to turn in your homework problems that I asked you to do. We're going to finish 2.5 on exponential functions, and then that's pretty much it. We're supposed to have 2.6 on this next exam, but there's just no way I can cover it in time. So what I'm going to do is just not put 2.6 on the exam. All right. So we will spend all of next class reviewing for the exam, which will be on Halloween, I think, right? Halloween's Tuesday? Yeah. So trick or treat. So if you look on our schedule, just make sure that when you're reviewing for the exam, it's only going to cover 2.1, 2.3, 2.4, 2.5. 2.6 will not be there, all right? All right. 2.1, 2.3, 2.4, 2.5. Okay, so because I'm going to have questions here that on the homework. Let me just go through this. This is what we did last class. We talked about exponential functions. We established that an exponential function is any function that you have a number raised to your variable. And that number, it just had two conditions on it. The number had to be positive, and the number could not be 1. So we could have an infinite number of bases, that's what we call this, for exponentials. We could have base 2, base 10, base 7, base 1/2. I think I gave you 1/5. Was that the one I gave you? 1/3? Okay, so as long as the number is positive and not 1, it qualifies as being an exponential function. Now, if the base is bigger than 1, you're going to have what's called exponential growth. So your graph will look like this, with a horizontal asymptote out the left side. You will also always have the point 0, 1 on the graph, no matter what, because if you plug in 0 here, any number to the 0 is 1. So that point is common to all exponential functions. Now, here, this is separate, okay? This is what happens if b is less than 1. So like on your homework, it was 1/3. Your graph should turn out looking like this. All right, and again, we have a horizontal asymptote. This time it's out the right-hand side. This is an example of what's called exponential decay. All right, so that's what we talked about last class. I asked you to graph too, right? Something like that. So now I'll entertain any questions on the homework. No?
Are you going to go over one?
I'll be willing to go over one.
All right. 43.
43. What page was that?
93.
Which one? 43? Okay. So for number 43, you're given the function f of x equals x squared minus x minus 6 over x squared minus 3x minus 10. Right? Okay, so what did I ask you to find here? X-intercepts, vertical asymptotes, horizontal asymptotes. That's all we wanted, right? So how do we find the x-intercepts? Set the numerator to 0, right? So we set the top of it equal to 0. And this is a quadratic equation, right? So you could use a quadratic formula or you could factor it. It's really your call here. Factoring, I think, is the most straightforward on this one. This would become what? X minus 3 plus 2. All right, and then you set each of those equal to 0. X minus 3 is 0, x plus 2 is 0, and you get two solutions, 3 and negative 2. So you could just put that, or if you want, you could write them as points, 3, 0, negative 2, 0. Either way, I'll take either one. That okay? That part all right? Okay. And then how do we find the vertical asymptotes? Denominator to 0. So same thing. Try and factor this. And this is what?
5 and 2.
5 and 2, but
It's
minus 5 plus 2. And so you get, set each of those to 0, you get 5 and negative 2. Now, the important thing here is that these are not points, okay? On your graph, these are those vertical dotted lines. Now, we're not graphing these, but these are points on your graph because they're x-intercepts, so you can write them as points. Here, you can't write these as points because they're not part of your graph. They're just those vertical barriers. All right, and then how about the horizontal asymptote? Here, what do you have to look at? The power on the top, we call that the degree of the numerator, it's 2. The degree of the denominator is also 2. What happens if they're the same? What do you look at? What? Divide what? The leading coefficients. The number in front here and the number in front there. You take those two numbers and you create a fraction out of them. And so you get, and you'll always write y equals, and then those two numbers, 1 over 1, which is just 1. So y equals 1. And that's it. Yes? Uh-huh.
So when I factored, I had gotten x minus 6 and x plus 1.
Where?
For the for the VA. Or sorry, for the x-intercept, just kidding.
Excellent.
Yeah, so I got 6 and negative 1.
6 and negative 1. Okay, yes, so this is actually, it can be a little tricky if you're not careful with your numbers. So if we look at this, you're saying minus 6?
Yeah, x minus 6 and x plus 1.
Minus 6 and then x plus 1. Let's just double check that. If you multiply here, you get x squared. Here you get plus x. Here to here you get minus 6x. And here to here you get minus 6. The problem is that these two together is negative 5x, right? And you're wanting negative 1. So common mistake. If we go back to this little thing that for factoring, what you're trying to do is find two numbers and multiply to be negative 6 and add up to be negative 1. So you're using the negative 6 here and the negative 1 there. And I agree with you that negative 6 and 1, they do multiply to be negative 6, but they don't add up to be your negative 1. So, yeah, yep. Okay, no, it's good. That's the type of thing you want to just get better at with time. At least you're doing that method, you know? I mean, at least you know what to do. That's a good thing. Okay, so at this point, I will take what you have. I will return this to you along with anything else I have next class. All right? So if you have this, turn it in. If you don't, you'll take a 0 on it, but it's not the end of the world. Just make sure your name's on it. Let's just try and get them all like to this table right here. I will not accept it at the end of class, so don't plan on doing it all while I'm up here and then at the end saying, oh, here's my homework. Okay? It's now or not, or now or never. Okay, is that everybody? Yes? Okay. All right, let's finish up exponential functions. So I just told you that an exponential function has to look like this, and that b has to be bigger than 0, and that b couldn't be 1, right? And that there were an infinite number of numbers that I could put there, right? But there's one very, very special one, a really special number, that if we put it there, it becomes this super function. And that number that I'm going to put here is actually this number. Now, That's a letter, not a number. But that letter represents a number. So let me try and help illustrate this. Do you all know what that is? Have you all seen that before? Pi. Have you all seen that? Pi is used when we're calculating circle stuff, right? Areas of circles, circumferences, things like that. We use this number pi. Does anyone know approximately what that number is? It's about 3.14. And it keeps going, 1.5. And the thing about pi is that it's a number that if you kept on going out, these numbers here would always change. Like there's never a pattern to them. As opposed to a number like if you take a number like 1/3, that number is 0.3333 forever, just threes, just keep going. So this keeps going forever, but there's a pattern, right? What I'm saying here is that this keeps going forever, but there is no pattern. It never repeats itself. In fact, the world record for memorizing how far this goes, like there's actually someone out there that can read out this number to 60,000 digits out of memory. 60,000. It took them, I think, upwards of 8 to 9 hours to do it. And this is, what do they call those people? Savants? Is that right? The savant? Yes? The savant? Anyway, this person that has that memorized, they don't look at numbers the way we look at numbers. They look at it a little different. I'll try and illustrate. Okay, so like if I asked you to describe to me your morning, right? You could probably tell me, okay, I wake up, I have a nightstand right here. It has a clock on it and a lamp on it. I get up, I step down, there's a carpet there. That carpet is tan. I walk into my bathroom. I've got a little dish with my soap. I mean, you could give me a very detailed description of your house, apartment, whatever it is, right? That's the way this person looks at numbers. It's like walking through scenery. And so each number is a shape and a color and an object. And so that they just memorize this journey through this thing. It's very different than the way we look at it. So anyway, this is a very special number. We call these types of numbers that keep going forever and never repeat, we call them irrational numbers. And the word irrational does not mean like, when you talk about like a person being irrational, like they're like, this person just completely irrational. You can't get anything across this person. It's not that. It's not. We're not saying like this number is just totally ridiculous. We're saying it's not a ratio. Okay, see this number 1 divided by 3? That's a ratio. If you take all the fractions that are out there, okay, you will create decimals. Like if I take 4/5, okay, this is going to be 0.8. All right, that's a decimal. This decimal stops. It does not keep going. This is a rational number. 1/3 is a decimal that repeats forever. It's a rational number. Numbers that cannot be written as fractions, that there is no fraction for pi, okay? If it was, I'd just tell you what the number is. The Chinese got very close. The Chinese used 22/7. That's what they use to approximate pi, but it's not pi. It's close to pi, but it's not. It's impossible to create a fraction that generates pi. So it's not a fraction, not a rational number. There's no ratio for it. It's irrational. Well, e is another irrational number that goes on forever and doesn't have a pattern. And it is approximately 2.71. Now, the value of this e, okay, this thing that keeps going forever, can't really be illustrated too much in this class. In calculus, we learn to understand that this e is the only number that behaves a certain way that we need it to behave, and so it's very valuable to us. So if we create a rational function, f of x, and we use that e as the base, so e is a positive number, right? 2.71, that's positive, and it's not 1. So it's fair for me to use that as a base. This right here is called the natural exponential function. And the word natural is coming from the idea that, again, what happened was in human history, we were trying to find a function that behaved a specific way. And we went looking and looking and looking and looking and looking, and we finally found it. And this is it, and this is the only one that does it. And so it just kind of naturally occurs. We can't explain why it is that way, but that's the one. All right? So we call it the natural exponential function. Now it's very useful in computations that involve finance, all right? Because it's a certain type of growth, all right? It's a certain type of growth. In fact, can you tell me if I were to graph this, would this be decay or growth? I just kind of gave it away. It'd be growth because the base is bigger than 1, right? 2.715. 2.71 is bigger than 1. So it should be growth if I graphed it. So if I were to ask us to graph this, you would do what you were supposed to do for homework, and you'd plug in those numbers that I told everyone to plug in, right? And so this first one would be e raised to the negative 3. This next one would be e to the negative 2. The next one would be e to the negative 1. What's e to the 0? E to the 0 should be 1. Remember we said anything to the 0 is 1. Then this one will be e to the 1, then e squared, and then e cubed, right? So how do we calculate that? How do we figure out what those numbers are? Well, we get our calculators out and we find the key on our calculator that has e. There's an e button on here. All of our calculators should have an e button. So if you have your calculator, now would be a great time to get that out. And if you don't have it, you need to bring it especially for the review and especially for the test. You will not be allowed to use your phone. Everybody's calculator is going to be different, all right? So your task right now is to try and find that E button on your calculator, all right? What you're looking for on your calculator is this E, not this E. Sometimes there's a double E on your calculator, not this one, okay? You're looking for E. And then what you want to do, let's do this one first because this one will be the easiest. Let's do E cubed. So see if you can figure out E cubed on your calculator right now. E raised to the third. If you can't, raise your hand and I'm going to come show you how to do it. This is your one opportunity to get help. I'll tell you what the answer is. It's approximately 20.085, something like that. I'm just going to put 20.08. So is there anyone that has their calculator that can't figure it out? I'll come show you real quick. Okay. So your E button is that blue one, right? So turn it on for, oh, it's on, never mind. Hit the blue, oh, clear that. Hit blue, then that button. Now it's saying E and it's even giving you the power. So put 3 there. There you go.
Thank you.
Good? You got it? Anyone else need help? Okay. If you don't need help, try and complete this table. Try and do all these. That means e to the negative 3, e to the negative 2. And I'll put the answers up here for you. Does anybody know what that EE was, that 2 E's? We use that for scientific notation, which is not what we're doing here, so don't confuse the two. All right, e to the negative 3, I'll go back up to the top here. You should get approximately 0.049. That's 497. Okay, I'll just put 49. E to the negative 2 should be approximately 0.135. E to the negative 1 should be approximately 0.367. We already know that this one is 1. E to the 1 is approximately 2.71. And then E squared is about 7.38. All right. Anyone have any trouble with that? Please let me know now. So these numbers aren't nice numbers, but we could graph them, right? We could approximate them, get a general feel for what's happening. Okay. It's very difficult for me to talk about E without the mathematician in me wanting to come out. So I'm just going to give you one more piece of information. I promise I'll move on. Have I talked about the stars at night? No? Okay. This is something that as a student I didn't really understand. Didn't make sense to me. Let's just talk about the numbers between 0 and 1. I did tell you about this, no? No? Okay. All right. Look at the numbers between 0 and 1. All of them, okay? Every number in there. If I were to just close my eyes and go in here and grab a number, what's the probability that you think that it will be a fraction? Good or bad? Do you think there's a good chance if I close my eyes and just grab a number that it's going to be a fraction? Okay, well, let's talk about the fractions. There's 1/2 in here, right? 1/4 is in here. 1/8 is in here. And basically, you can start looking 3/4. I mean, there's an infinite number of fractions in here, isn't there? Infinite number. So if I close my eyes and just grab one, the probability that it's a fraction you think is pretty good? Yeah? Okay. Now, I just told you that there's also irrational numbers. I gave you 2 examples, pi and e. Those were 2 examples of irrational numbers. These are numbers that you cannot write as a fraction. So if I close my eyes and reach in here, what do you think the probability is that I pull an irrational number out of there? Good or bad? Bad? Good? What do y'all think? The same? 50-50? Maybe there's as many fractions as there are irrationals in here? That's a good guess. There are an infinite number of irrationals also. So you've got an irrational number of fractions an infinite number of fractions and an infinite number of things that aren't fractions. But it actually turns out to be something kind of mind-blowing. If you close your eyes and you reach in here and you pick out a number, the probability that it's a fraction is 0. You have no chance of pulling a fraction. No chance. Which means that there's more things that aren't fractions in here, but there's an infinite number of fractions. How can you have more than do you see the little conundrum here? It turns out that there's 2 types of infinity. So there's what we call countably infinite and uncountable. So this gets complicated, and this is all based on what's called measure theory, and I'm not going to get into details. I have a better example for you. So have you ever been way out of the city at night? Yeah? You look up in the sky, you're like, holy shit, those stars, look at all those stars out there, right? Okay, so you look up, and you're just like, wow. Like we just recently moved and we're a little bit further out of the city now, and I can actually see the Milky Way. I can actually see the actual strip, the one band of the Milky Way, which is pretty awesome. So you see all these stars. Think about the fractions in here as being the stars, all right? They're all over the place. Think of the irrational numbers as being the darkness in the sky. So if you were to just randomly like point into the sky, the chances that you are pointing directly, now I'm not talking like your finger, I'm talking like a perfect straight line that would go out, the chance that you're going to point directly at a star is infinitesimally small. The chance that you're pointing into darkness is almost assured. That's the same sort of thing. As I'm reaching in here, the only way I could actually get a fraction is to go and say and look for it. Then I could get it. I'd have to open my eyes and go look. Then I could actually find it, if that makes sense. Okay, so the only reason I like to give that little speech on it is because when we put these numbers, e, pi, square root of 2, when I was a student, I thought, okay, the irrational numbers, there's only a few of them, okay? And then everything else is fractions. But it's actually the other way around. There's so many more of these than there are fractions, all right? So, all right, let's move on. Okay, we want to do something, we're going to kind of switch gears here. And we're going to do an application of exponential functions with finance. And this has to do with what's called simple interest. Okay, so if you go and get a credit card, I'm not going to ask if you have a credit card, but if you have a credit card, you pay a certain percentage, right? Or if you borrow money from the bank, they're going to give you the money, but then you're going to have to pay it back more than they loan you, right? Or if you put your money in the bank, right? If you have money and you go put it in the bank, they'll actually give you money for your money, right? So the way it works is you got bank, right? You got the people who got the money, and you got the people who need money, right? So what happens is the people that need money go to the bank, and the bank gives them money either in the form of a credit card or a loan or something like that, right? You want to buy a car. So they loan you the money. And let's just say for a simple example here that you're going to borrow $1,000 from the bank, right? They're going to charge you interest on that money. They say, okay, here's the $1,000, and we're going to charge you interest. Now, if you do a credit card, the interest is what? Like probably 20-something percent. Okay, so I'm going to put here for a low number 15%. And then they say like annual percentage rate or something like that. That's like, it's a little complicated, but let's just go with this. 1,000, 15%. So at the end of the day, you're going to pay back more than you borrowed, right? Okay. Now, the people who have the money will go and put the money in. So let's say this person has $1,000. They want to go put it in the bank. And the bank says, all right, we're going to take your money, thank you very much, and we're going to give you some money for your money. Now, how much do they give you? What percent do they give you? Not even 1% usually. It's not even 1%. Used to be you could get banks around 2%, like 3%. Like probably about 10 years ago you could do that. Before the big old financial collapse and banks realized that people are basically living off their credit cards, like food, gas, everything is just on credit. So anyway, they do like, I'm going to say 1%, but it's usually less than that. Okay? Is what they get back. Okay? So you see where the bank makes their money? Right? They're borrowing someone's money to loan it to somebody else. These people are paying back more than they borrowed, but they're only kicking these people a small percentage back. Now, the problem is that if all these people come one day and say, hey, give us all our money back, the bank won't have it because it's all loaned out, right? So that's why banks are insured up to a certain amount. So if like there's a huge financial crisis and all these people come running for their money, the federal government will come in and make sure these people get their money up to a certain amount. So that's the way it all works, all right? Now, what we want to do here is set up a formula that we use to figure out, like, how much is that person going to owe back, right? After a certain amount of time, how much do they owe? How do we calculate these things with these percentages? And what all institutions use is basically one of two formulas, and they're called the simple interest formulas. And here's what they look like. The first one, just write it down for right now, and then we'll talk about what everything means. I actually had to think about it for a second. Okay? That's the first one. And then the second formula is what I like to call the shampoo formula, because there is a shampoo out there called PERT. There is. And I had my wife buy it for me about a month ago because I just wanted to look every time I looked in the shower, I wanted to see that formula so I wouldn't forget it. It used to be called PERT Plus, but now it's just PERT. All right, so there's our PERT formula. This is some other weird formula. Now, when you use these formulas, there's like one little piece of the wording that tells you which formula you're going to use. But I need to identify what all these letters are because it looks a little bit overwhelming, right? So let's first start out with what the P represents in both formulas. P is the amount you start at. This is also known as principal. So this would be the $1,000. Whether or not you're borrowing it or you're giving it to the bank, doesn't matter. The amount you start at is the principal. All right? The next number, let's go with R, because it's in both formulas, right? So P is here, P is here, R is here, R is here. This is the interest rate. And just be careful with interest rate, because when you're using the formula, if it's 15% interest rate, you have to convert that to 1.5. Sorry, 0.15. I don't know what I just did. 0.15. If it was 3.5% interest rate, you would convert that to 0.035. So remember, when we're converting percentages to decimals, we take the decimal point and we move it 2 places to the left. If it's 15% and you plug in 15 here and 15 here, you're going to get an incorrect answer. It must be converted to a decimal. Understand? Okay? What else is in here? Let's go with T. T's in both formulas, right? T's time. And it's always measured in years. So why is time important? Well, let's say that you're going to borrow money from the bank, $1,000 at 15% interest, and you're going to borrow it for 4 years. That means you're going to have to pay it back in 4 years. Then we need to know that, because how much you owe at the end of 4 years is going to be different than how much you would owe at the end of 2 years. All right, so T is time in years. What if you borrowed money for 6 months? T would be 0.5 or 1/2, however you want to do it. All right, so you have to pay attention to that in the wording of the problems. All right, so P's in both, R's in both, T is in both. How about A? A is in both, right? A. So A is the amount at end of time. Not end of time like end of world, end of days. I'm saying end of time, this time right here. If your time is 4 years, the A gives you how much is there, how much you owe, or how much you've gained at the end of that time period. All right? So that's, both of these formulas will tell you how much you will owe the bank after a certain amount of time, or if you're loaning money to the bank, it'll be the amount of money that you have now because they've paid you something. All right? So that's what both these formulas give us. The only thing I haven't given you is what? The n. And the n only appears in the first formula, right? It does not appear here. The n is kind of a special value. What it is, n, is the number of times interest is compounded per year. And that will normally be given to you in the problem. So let me try and explain what that n is, because it's somewhat complicated. It can be confusing to students. Okay, let's say we're that person who borrowed the $1,000, right? What they could do, the bank could do, is they could just, at the end of the year, charge me 15%, right? Yes? At the end of 1 year, they could charge me 15% of the $1,000 I borrow. That would mean that they actually calculated the interest one time, which means n would be 1. The bank could also do it this way. They could do it, let's say, like the first 6 months. After the first 6 months, they calculate interest, and then after another 6 months, they calculate it again. So they do it twice a year, right? That would be n is 2. They could do it monthly. Every month, at the end of the month, they calculate the interest. Next month, calculate the interest. Then what would n be? 12, right? Now, what do you think would be better for the bank? To do it once at the end of the year, or do it twice a year, or to do it 12 times a year? Probably the more they do it, the more often, the more frequently they do it, the more you're going to owe them, right? Yes? And it does turn out to be that way, but it's not like a dramatic difference. We're going to do some examples and we'll see the differences. But because when I say they do it one time at the end of the year, they do it once on the entire amount. If they do it twice a year, they do it at the halfway point, but they do it on half your money. So they only calculate the interest on half of what you have in there. So it doesn't accumulate as fast as you would think. If they do it 12 times a year, they're going to do it at the end of the month on 1/12 of your money. So does that kind of make sense? It's not as impactful as doing it, 15% on the entire amount, 12 times a year. That would be ridiculous. All right. I think that's it. Oh, I need to tell you, how do you know when to use these formulas? Like, when do you use this one? When do you use this one, right? So this one, you use this, use if compounded rate is given. So if they tell you, hey, it's compounded 12 monthly, then you would use that formula. If they say, hey, the interest is compounded weekly, you would use this formula. If they say it's compounded quarterly, you would use this formula. So this formula, you use this if it's compounded what we call continuously. Continuously. And this is always a very kind of strange idea for students. This formula is the formula that banks use, and what it does is it's compounding your interest at every instant all the time. So it's like, it's not daily, it's not hourly, it's not every minute, it's not every second, it's at every instant. It's constantly compounding or calculating your interest. But the deal on that is, if they're going to do it, if they're going to compound your interest an infinite amount of times, then that means they're going to do it on an infinitesimally small part of your money. It's really complex. It's basically this formula right here, letting n go to infinity. And if you let n go to infinity here and here, e pops out. E is what happens. So that's why e is such a special number. It's because it's what happens when you take something like this and let this number and this number get huge. It approaches e. All right? All that you really are going to want to care about is, give me a problem and let me calculate, right? All right, so you ready to do one? Okay, I want to do a problem that'll pique our interest a little bit, because we've been talking about lottery, right? Didn't we talk about the lottery a while back? Let's just see how good life is for someone who hits the lottery. Okay? Instead of talking about credit card debt and all that stuff that would get you all depressed, right? Let's talk about the lottery. So let's say that we hit the lotto, all right? You win lottery and take home after taxes, okay? So we've already pulled the taxes, so they're going to take at least half of your money, right? So how much do y'all want to have won?
What was the biggest jackpot? 400.
Yeah, but at 400 million, we're not even worried about interest. I mean, we could just go throw $1 million out the window and be like, who cares? So let's make it more reasonable. Something that would make you question, if you won this much, are you set? You know what I'm saying? Like, are you good? Or are you going to need to still maybe do some work? 500? Let's go with the million. A million's a nice round number, right? Let's go with $1 million. I mean, so you really probably won like 2 point something million. Taxes were taken out. You got $1 million. Now, here's our goal. We're going to put this. You know, you'll probably get someone who would advise you financially on what to do with the money, but we're going to be very conservative here. And we're going to say we're not going to throw it all in the stock market. We're going to do some mixing up of money here and there. But let's just say on average, we plan on making about 3% interest on this money per year. All right? So that means maybe you got some in the bank, you got some in CDs, you've got some in the stock market. But let's just say on average about 3%. All right? You plan to invest and earn 3% interest. I think 3% is fair. Okay, I think that's a fair number. You could probably invest properly and get about 3%. Stock market, you could make a lot more, but it's riskier, right? You could lose your money too. So, all right. So, what do you want to know? Do you want to know how much you'd have if you just left that money in the bank for a year? Yeah. Let's just see what it would be like. Okay. How much is in bank after 1 year? And then I'm going to give you two problems here. First of all, part A, if interest is compounded, I'm going to give you three problems. Compounded monthly, part B, if interest is compounded daily, and then part C, if interest is compounded continuously. So depending on how your money is invested, it would depend on which of these formulas they would use, okay? Most institutions do continuous compounded. Most institutions, because it's easier to calculate. It's easier on the computers, for the computers to do this. Not really the computers, it's really people who have to deal with the formulas. This is easier to mess with, that PERT formula. Okay, everybody understand what we're doing? Okay, let's do part A first. I'm going to have to erase all this. Part A. Let's identify some pieces for part A. For part A, what formula are we going to use? The first one or the second one? First one. A equals P parentheses 1 plus R over N raised to the NT. All right, let's identify the pieces we have. Do you know what P is? 1 million. That's what you start with. So that's 1 followed by 6 zeros. All right. Do you know the rate? The rate. 3%. So what am I going to use in the formula? 0.03. Okay, good. Do we know the time we're going to leave the money in there? 1 year. So 1, right? And then do we know N? It's compounded how often? Monthly. So it's just going to be 12. Let me point something out here so that you don't get hung up on this. What if we were to leave it in the bank for 2 years? All right, 2 years, N would still be 12. It does not turn into 24. N is always just the number of times they compound it per 1 year. So even if T was 5, this would still be 12. Understand? Okay, so T has no impact on N. All right, so now what I'm going to do is just plug everything in this formula. I have A equals 1 million, parentheses 1 plus 0.03 over 12 raised to the 12 times 1. Now we have to make sure we do our order of operations correctly here. You're always supposed to do what's in parentheses first, right? So I need to do this. Inside here I have addition and then I have division. So I'm going to do the division first. So on my calculator, I'm going to do 0.03 divided by 12, and I'm going to get a pretty decent number actually. It's 0.0025, all right? So this right here is 0.0025, and now I'm going to add 1 to it, right? So I'm going to write the next line. It's 1.0025. And then I'm going to raise it to what power? 12. 12 times 1 is 12. So I have 12 here. So order of operations, we do not multiply these two together. Not yet. We actually have to do exponents before we do the multiplication. So I'm going to, on my calculator, take 1.0025 and raise it to the 12th power. Does anybody need help on how to do that raising the power? Sure? Somebody want to share with me what they got? You got 1.03. Now, with these financial computations, I want you to go out as far as your calculator goes out with the decimals. Because if you round like that, it's too much. That's too much rounding. You actually need it to be more precise than this. So 415,957. So if yours goes out further, just write them all down. If yours goes out a little less, just write down what you have. So that's taking 1.0025 and raising it to the 12th. Now take that and multiply that times 1,000,000. And you get what? Yeah, it moves decimal. So 1,030,415.9. Now this one I'm going to round to the nearest 2 decimal places because this is money now, right? So I can only really go to the cent. So that's what? $1,030,415. So that means really, if you want to look at it this way, if you put $1 million in the bank and you get about 3% back on your money, after a year you got $30,415 more than you started with, right? So is that enough money for you to live on? That depends on you. Like, would you be happy making $30,000 a year? I mean, maybe. You let your money sit there and you just live off that interest? What would happen if this was $10 million instead? All that would happen is that everything would move over 1 decimal place. So how much would that person make? $300,000 a year. You gonna live off that? You okay with that? What if this was $100 million that you won? You'd be making $3 million a year on interest. Right? That's crazy. So these people who hit these lottos that are like 400 million, right? If they invest their money properly, even being very conservative, they can make millions of dollars a year off their money without touching it. It just sits there. That's the whole power of, you've heard that, like the rich get richer and all that stuff. I mean, you got a big, big egg that you're sitting on and you're loaning that money out to other people, right? They're paying you for that money and you can just live off that. So you think about these billionaires, right? These billionaires that just have money invested in different places, they get money back. They're never even tapping into that money because they're just living off of the interest. All right, so if you ever win the lotto, I just want a little piece, just a little piece. You can come give me just a little piece.
Are you going to give us an A in class?
Pardon, what?
Would you give us an A in class right now then?
You go hit the lotto first and we talk, okay? I'm not going to commit to anything yet. If it's big enough, we'll work it out.
You need a ring on your fridge?
All right, we're going to do part B now. Okay, so for part B, what formula are we using? Same one. What's the only thing that's changing for part B? It's compounded daily now, right? Daily. That means the only difference is n. So n now is what for us? We'll go with the standard year, okay, 365. Banks, a lot of times banks don't use 365. They use like 360 or something like that for holidays. I don't know. We're just going to go with the standard year here. So let's see how our formula looks now. It's A equals a million's here, and then 1 plus 0.03 over 365 raised to the 365 times 1. Now, what I said is happening here is that they're now compounding. Instead of just every month, they're doing it every day. And so you'd think that this impact of that would be dramatic. But as we're about to see, it's not as dramatic as you might think. Okay, so I'm going to take 0.03, I'm going to divide it by 365, and I'm going to get a crazy decimal here. Is anybody getting this on their calculator? 8.21917, blah, 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 and then e negative 5? Anybody get that? No? Okay, if you got this, what this means, this little e negative 5, means you have to take that decimal and move it 1, 2, 3, 4, 5 places and put zeros here. And that's the number we're working with. So it's actually 0.0000821917. That's the number. Now, how many of you got that, not this? Got this one right here. Good. Okay, so your calculator already is doing this. This is called scientific notation. You can change your calculator's mode so it spits this out instead, but I'd have to show you how to do that. All right, this number right here is just this divided by this. Now I need to take that and add 1 to it, right? So I'm going to have equals a million, and then I have 1.1234 zeros, 821917. And I'm going to raise that to 365. So like I said, use all the decimals you have there. 1, 2, 3, 4, let's see, 821917. I'm going to raise that to the 365. And so my next line says a million times 1.030453233. That's what I got when I took this and raised it to the 365. And then multiply it by a million, and you should get 1 million. Let's see, 453, so what was the previous answer, part A? 400 what? 415. This is 453. So we made a little more money, right? Made a little more money, but is it as dramatic as you thought it would be? It's not. It's not. Now let's do the compounded continuously. That's part C. So for part C, there is no n. And the reason there's no n is continuously means n is infinity. But when that happens, we get a new formula. So for part C, we're using the Shampoo formula. A equals pert. So this is going to be a million times e raised to the 0.03 times 1. Right, because t is 1, time is 1 year, the rate is 0.03. So if you were going to do this on your calculator, you first figure out what this is. In this problem, it's pretty simple because it's times 1, right? But if this were 2 years, if that were 2 years, you would, oh, it's the computer. If it were 2 years, you would have to do 0.03 times 2 first, okay? 1 million e to the 0.03. Now do this on your calculator, e to the 0.03. And that's what I was having you do earlier. So make sure you can do e to the 0.03. And that number is going to look pretty close, pretty familiar to the number that we've been getting. It's 1.030454434. That's what I got. And now multiply by 1,000,000, and you'll have $1,030,454.34. Now look, when you do this on the test next Tuesday, if we're off by a little bit, that's okay. If we're off by a couple of cents or a dollar, it's fine, because we're going to round differently. But if you're off by like, $20,000, then obviously there's something wrong in your calculation. So the answer for part A was this with 415 or so. The previous problem, what was it? 453. And if we compound continuously, it's only $1 more or so, right? Anybody have trouble getting this? Not quite sure you'd want to quit your job and start buying a bunch of stuff with $1 million, because it'll go fast.
You said that like people who need money, they compound. It's better to compound it more times.
No. So look, do you see how compounding it continuously gave us the biggest number? But it wasn't like dramatically bigger, right? So banks use this formula because banks, when they loan out money, right, they want that to be the biggest number.
Right.
But they also pay the people who loan them the money
That's
that high amount.
Is it two separate?
No.
Or is it the same?
They use the same thing. They use the same thing.
Okay.
Yeah. Yes.
So at the beginning of the next year, that's going to be your principal?
Yeah, so that's a great question. This would be what you start with. So let's say you put this money in the bank and you don't touch it for 5 years, right? Okay, think about that for a second. You put this money in the bank and you don't touch it for 5 years. In the first year, how much money did you make the first year? $30,454. Does that mean in the next year you're going to make $30,454? No, you're actually going to make more money because you're starting, it's almost like you have a new principal, right? So if you want to answer that question, here, how about we do this? Change this, you want to go 2 years or 5 years? 2? Okay, let's go 2 years. If I change that to a 2, then this number right here becomes 0.06, and then I have to change this number. So I need to go get on my calculator and do e raised to 0.06. And so now this number becomes 1.061836547. And then this number, when I multiply 1 million times this, I have $1,061,836.54. So in the first year, I made about 30,500. What's 30,500 plus another 30,500? 61,000? But see, I actually made 61,800. So it's more than, we're not just doubling this amount, it's a little bit more. Does that make sense? So yes, this number right here would actually act like a new principal. So if you're willing to not touch your money for a while, maybe finish your education and just put that money aside, then it'll grow. That's why they say if you start a college fund for a kid at a young age, right? Like that can grow very fast. This is the way you do retirement too. You put a little bit of money away and it continues to grow. Let's do something a little different. Just out of curiosity, my own curiosity.